Hi everyone. In yesterday's class we learned how to do integration by parts, which is section 8.2 in your textbook. And we learned how to do this by using the formula the antiderivative of u dv is equal to u times v minus the antiderivative of v du. And we use this when we have a product. Okay, so if we take a look at number 1, we've got the antiderivative of e to the x cosine x dx. So it definitely follows the pattern where we're taking the integral of a product. Recall also from yesterday that we used the acronym LATE to help us decide what to set u equal to. Our first choice would be a logarithmic expression. Second choice would be algebraic. Third would be trig. And the last one would be exponential. And for us, that's going to show up as e to the x. So in the problem, number 1, by the way, just move number 2 to the back of the page. You're going to need lots of room to write for both of these problems. All right, so on number 1, I see a trig function. So we're going to set u equal to cosine of x. And then we take the derivative of both sides. So we have du is equal to the derivative of cosine x, which would give us negative sine x dx. So we need all three of these things when we go to apply our formula up here. We need u, we need du over here, we need u right here. Okay, recall also from yesterday's lesson, the remaining parts up here are going to be what we use for dv. So in our first problem, we have dv is equal to e to the x dx. Okay, we need to work backwards or find the antiderivative in order to solve for v. So we're going to take the antiderivative of dv and set that equal to the antiderivative of e to the x dx. So we're going to just do both of those. So on the left side we get our v. On the right hand side, the antiderivative of e to the x dx is just e to the x. So we're going to hold on to that. Okay, the next step, plugging everything into our formula. So we have our original function, our original problem, the antiderivative of e to the x cosine x dx. And now we're going to set that equal to u times v. So we want to take u times v. And you can write it as cosine x times e to the x. I'm going to put that e to the x out in front. And then from that we're going to subtract the antiderivative of v times du. So we're going to have v, which is e to the x, times du, which is negative sine x dx. And I'm going to take a second and clean that up. So we get e to the x cosine x minus, and I can also bring out a negative because we have this, we're subtracting. We have this minus sine x, so that's going to turn it into plus the antiderivative of e to the x sine x dx. So any negatives I would bring out in front of the integral sign, but also any coefficients, any numbers that you have, you can bring out in front too. Okay, but notice what's left here in this integral is a product. Okay, so we have to do integration by parts a second time. So let's move this up a little bit. And we're going to start off by selecting our u value, which would be the trig portion here. So we're going to say u is equal to sine of x. And that will give us du equal to cosine of x dx. So we'll need this in a minute, and we'll need this in a minute. Okay, so the remaining part in here, the e to the x dx becomes dv. So we have dv equals e to the x dx. Okay, we want to take the antiderivative of that. So do the integral of both sides. And the antiderivative of dv is going to be v. Antiderivative of e to the x dx gives us e to the x. Okay, so we need to keep this portion This is part of our final answer, so we're going to bring that down. I'm going to write the original problem first. We're going to try to fit all this in there. Here's the original. Antiderivative of e to the x cosine x dx. And then this portion, e to the x cosine x. And to that we're going to add what we get from this part right here. So we need to do u times v. And notice that it's sine x times e to the x. So let's write that e to the x out in front. It's a little messy, so let me clean that up just a bit. Make sure that you can read it. So we're going to write e to the x sine x. And from that we have to subtract the antiderivative of v, which is e to the x, du, which is cosine x dx. Okay, so here's the issue. It feels like we're kind of going in circles, and we kind of sort of are, but notice that what we have here on the left-hand side is, sorry, that was the right-hand side. Notice that that is a match with what we have here on the left-hand side. We kind of got back to the original. So in the process of doing this, we've created like terms. So what we need to do is think of this as being A, capital A, and this would also be capital A that we're subtracting. And think of this term, the second term here, as being B, and this term as being C. We're going to do a little bit of algebra. So I'll just show you here and describe it, and then we'll actually do it with all the integrals. We're going to take and add A to both sides. So that would create the equation that says 2A is equal to B plus C. Now remember, we want to solve for A. We want to know what this integral is equal to. So we're going to divide by 2. Divide by 2. So our final answer is going to be A is equal to B plus C divided by 2. All right, we're going to go back in and substitute our integrals back in to write the final answer. So A was equal to the antiderivative of e to the x cosine x dx. And now that's equal to b plus c all divided by 2. So b was equal to e to the x cosine x plus c, which was equal to e to the x sine x. Now, since we're working with a general antiderivative, we need to include something else at the end here. I'm just fixing that real quick. We have to say plus c, because it's a general antiderivative. All right, so we used integration by parts twice, and then we worked until we saw a like term. This was back to our original, so that was really key. So we could combine those like terms together and then solve for that integral just using a little bit of algebra. Okay, and our second example for today, we have the antiderivative of e to the 2x sine 3x dx. So a couple of things about this. Notice that it's not just e to the x, so we are going to have to use a u substitution to find the antiderivative of e to the 2x. And also notice that it's a sine of 3x and not just sine of x. So we're going to get into the chain rule. Okay, so there's a lot going on. All right, we're still doing the integration by parts process, so we do need to identify u. So we have an exponential piece and a trig piece. So u is going to be equal to the sine of 3x. So we have u equals sine of 3x. And then we want to take and find the derivative. So we have du equals the cosine of 3x. And this is where the chain rule comes in. So it's cosine of 3x times the derivative of the inside, and the derivative of 3x is just 3, and we need a dx on the end. All right, you guys, you know that we're going to rewrite that with that 3 out in front. So du is equal to 3 cosine of 3x dx. I have a little bit of trouble writing with the stylus today. Let me try that again. So it'll be 3 cosine 3x dx. Okay, so there's u. Just going to highlight it so I can find it a little bit easier later. All right, the remaining portion of our original problem becomes dv. So dv would be equal to e to the 2x dx. Okay, and we are going to find the antiderivative. So write it and then we'll talk about it. So antiderivative of dv equals the antiderivative of e to the 2x dx. Left-hand side, that's how we get v. The right-hand side, this is what I was referring to. We know that the antiderivative of e to the x is just e to the x. So there is going to be e to the 2x in here. But if you take the derivative of that, we wouldn't get e to the 2x back. And so we'd get e to the 2x times 2 back. So here's where I suggest that you do this by a u substitution. So I'm just going to say u sub. Let u be equal to 2x. So du is equal to 2 dx. So 1/2 du is equal to dx. Okay. So if we rewrite our integral as the antiderivative of e to the u du, notice that we have to put 1/2 out in front because the dx right here would get replaced by 1/2 and du. So I have the du, I need to put the 1/2 in there. If you take the antiderivative of this, you're going to get 1/2 e to the u. And substitute back, we get 1/2 e to the 2x. Okay, this is going to show up a lot. Okay, so if you could just keep this in mind, that when you do the u substitution for this particular type, when you have that exponent on e is something times x, you're always going to have 1 over the number times e to the 2x in this case. So you wouldn't necessarily have to show me this process every time. Okay, so this is our v value. All right, so now plugging it into the partial integration formula. So we're going to take this integral, e to the 2x sine of 3x dx, and that's equal to u times v. So we're going to take the v, I'm going to put v out in front, 1/2 e to the 2x times sine of 3x. And we're going to subtract from that the antiderivative of v, which is 1/2 e to the 2x times du. Okay, so I'm going to try to squeeze that in there. And that du is equal to 3 cosine 3x dx. Okay, we're going to have to get this cleaned up. Okay, I'm going to just leave this off for now because I need more room to work here. So we have 1/2 e to the 2x sine of 3x. Okay, minus, now we're going to bring a constant out in front. So I know I could bring this 1/2 out in front, but I also have this 3. So what I'm going to bring out in front is the fraction 3 over 2. And then we have the antiderivative of e to the 2x cosine 3x dx. Okay, so we've done the work, the process of integration by parts one time through, and notice that this integral is not the same as the original, so we're going to try it a second time. Okay, with the second time through, we are going to let u equal cosine of 3x. So we have u equals cosine 3x. Then we would have du is equal to 3, negative 3 sine of 3x dx. Because the derivative of cosine x, cosine of 3x would be negative sine of 3x times 3, because we have to use the chain rule for that. Okay, next we have to figure out what dv is equal to, and dv will just be equal to the e to the 2x times dx. So dv equals e to the 2x dx. Now we do want to take the antiderivative of both sides. We want to solve for v, so do that integral. Remember, just up above, right up here, we did the antiderivative of the same thing, e to the 2x. We did the u substitution. Remember that I said that you can take that shortcut. You can do 1/2 e to the 2x. And you can always check it by taking the derivative and verifying that that'll get you back to e to the 2x. Okay, so now we need to use the little formula, u times v minus the integral of v du. Keep this first part. I'll try to write it as neatly as possible. This gets pretty big. So we have 1/2 e to the 2x sine of 3x minus the 3/2, that constant, and we need some brackets here because this is the piece where we have to do u times v and so forth. So we're going to take u times v, so you have cosine 3x times 1/2 e to the 2x. I would rather see the 1/2 e to the 2x out in front, and then cosine of 3x minus the antiderivative of v, which is 1/2 e to the 2x times du, which is negative 3 sine of 3x dx. Okay, like always, we are going to try to clean this up a little bit, make it a little bit smaller. So bring down that first part, 1/2 e to the 2x sine of 3x minus 3/2. I'm going to hold off on distributing that just yet. 1/2 e to the 2x cosine 3x. We're subtracting the integral, but we have a negative in here that we could bring out, so it's going to turn into a positive. We also have two constants, the 1/2 right here, and that 3. 1/2 times 3 will give us positive 3/2 that we can bring out. Then we'll have the antiderivative of 1/2 e to the, not the 1/2. We'll have the antiderivative of e to the 2x sine 3x dx. Okay, next, let's slide this up a little bit, and we do want to distribute into the brackets there. So bring this down one more time. 1/2 e to the 2x sine 3x minus, well, the 3/2 times that 1/2 will give us 3/4, negative 3/4 e to the 2x cosine 3x. Here we're going to distribute. We have a negative times a negative 3/2 times positive 3/2, so negative 9/4 times the antiderivative of e to the 2x sine 3x dx. Now, I know you can't see it here, but because I didn't have room to write it over here, but the original problem is this integral right here. So on the left-hand side, we have 1 times the antiderivative of e to the 2x sine of 3x dx. And on this side, we have negative 9/4. So what we're actually going to do is bring this to the other side of the equal sign by adding it to our original equation. So we're going to say plus 9/4 times the antiderivative of e to the 2x sine 3x dx. And that's going to be equal to these two terms. So it'll be 1/2 e to the 2x sine of 3x minus 3/4 e to the 2x cosine of 3x. At the end we'll put our plus c. Okay, these two, like I mentioned, they are like terms. It's the antiderivative of e to the 2x sine 3x dx in both cases. So here we have 1 times that integral. Here we have 9/4. So 1 plus 9/4, we'll convert this to 4/4. So you can add them together, and that'll give us 13/4 times the antiderivative of e to the 2x sine of 3x dx is equal to 1/2 e to the 2x sine of 3x, minus 3/4 e to the 2x cosine 3x. Okay, last thing that we need to do is to eliminate that 13/4. So we would multiply both sides by the reciprocal, and that means you're going to multiply each of these terms by 4/13 and simplify. Okay, so squeeze that in there because I'm running out of room. So we're going to do times 4/13. Okay, so you have the antiderivative of e to the 2x sine of 3x dx is equal to 2/13 e to the 2x sine of 3x minus, and we have to multiply 4/13 times negative 3/4. It'll be negative 3/13 e to the 2x cosine of 3x. And because we are finding a general antiderivative, we do need to put that plus c at the very end. Alright, good luck on the homework tonight. It is just 3 problems. We'll probably have time to go over at least one of them in class tomorrow.